All right, we're jumping into part 2 here. We're going to look at least 2 examples. There is a third one, but I don't know, I might just show it to you in the book because it's a little bit much to write out. Here's a really simple example, though. So this is how your homework questions and test questions are going to look for this section with Taylor series. So let's say you're given a function f of x is equal to 1 over x, and you're also given the centering location. So you're going to be given a is equal to 2, and we want to find the Taylor series, and we also want to know where does it converge. So not just finding the Taylor series, but picking out where the Taylor series converges as well for a given function. All right. To do that, we're going to be using the definition for Taylor series. So I still have it above here. I'm just going to scroll up to it real quick to remind us. So here is the formula for Taylor series. Make sure when you go to take the test here on Chapter 10, which is going to be coming up here pretty soon, that you have this formula written down somewhere near you. So here the infinite series of the kth derivative at our center divided by k factorial times x minus a to the k. And here's just a few of the terms written out. Okay, so I'll copy paste this down here just so we have it close by. Okay, remember that our function is 1 over x. If I want to plug stuff into my formula here for Taylor series, I need to find the derivatives. Well, we don't have to find all of the derivatives because there's an infinite number of them, but let's just find at least 3 or 4 so we can get a general idea of what the derivatives are going to look like. So just writing stuff down, our function is 1 over x. Let's take the first derivative, just generically at x. You can think of this as being x to the negative 1. So we would bring down that negative 1, and then we would take 1 away from the exponent, so we get negative 1 over x squared. I'm not going to write it like that, though, just because I know what's coming up here in the future. So I'm going to leave it like this, negative x to the negative 2. It'll make taking the derivatives easier anyway. Second derivative is that this exponent negative 2 is going to come down. Negative 1 times negative 2 is positive 2. And then again, we're going to take 1 away from the exponent to make it negative 3. So maybe one more. So then the third derivative, we would bring down the negative 3. It would be a negative 6, and then take 1 away to make it a negative 4. Let's write out what this would be generically, though. So if we went all the way down to the nth derivative at x, let's talk about the coefficient out in front. It started at positive 1, and then it went negative 1, positive 2, negative 6. Notice that it alternates positive, negative, so we are going to have an alternating term out in front, negative 1 to the n. The next thing is the value of the coefficient out in front, 1, 1, 2, 6, and maybe you can see the pattern. If I were to take the derivative one more time, I'd be multiplying that 6 by a 4. This is a factorial sequence here. So 0 factorial on the 0 derivative, 1 factorial on the first derivative, 2 factorial on the second, 3 factorial, and so on. So we are going to have an n factorial in my nth derivative here. We got to be a little bit careful about what the exponent would be. We're starting at negative 1, and then we keep going down by 1 every single time. So you can think of it as negative 1 as our starting point, and then every single time we subtract away n. Okay, so I'll leave it like that. You could factor out a negative sign from these if you really wanted to, but it wouldn't really look much nicer. Okay, so this is just the generic form of the nth or the kth derivative, but remember we don't care about what it is at x. From our Taylor series formula, we need to know what these are at the centering locations. So I'm just going to repeat that process, but now we're going to be plugging in 2 into all of these. So if I plug 2 into the original function, that's going to give us 1/2. If I plug 2 into the first derivative here, that's going to give me a negative 1/4. Okay, maybe one more, and then we'll do the generic one. So, oh no, sorry about that. If we plug 2 into the second derivative here, we're going to have a 2 on top divided by 2 cubed, which is 8. So this is going to be, yeah, 1/4 again, it looks like. And then so on and so forth. Okay, so let's plug it into the nth derivative, plugging 2 into that. So we're going to get this negative 1 to the n. again, this just decides if it's positive or negative, and we don't know what that's going to be because we don't know which derivative we're taking necessarily, just that it alternates. The even derivatives are going to be positive, the odd derivatives are going to be negative. We're going to have that n factorial out in front as well, and again, that just depends on whatever the n is at the time. And then we're going to be, I'll go ahead and divide here, but we're going to be dividing by 2, and then if I'm dividing and putting that in the denominator, that's going to make that exponent positive, so it's going to be 2 to the n plus 1. Okay, great. So this is going to be just the generic form of my nth derivative here. Now we can plug it into the Taylor series. So what the Taylor series is going to say for us is that this is going to be the infinite sum, k going from 0 to infinity, of this term. This is the nth derivative at 2. That's this top numerator up here. So let me just copy this down. So we have that negative 1 to the n. We have the n factorial, and we're dividing that by 2 to the n plus 1. Oh, it didn't like me. I'll put the n factorial there instead. Okay. And remember, it's going to be this thing, which is the top numerator here, divided by another factorial. I should have been a little bit more careful about using k's here. Like, these are supposed to be k's and not n's, but I don't really feel like going back and changing it. All right, so our infinite series, well, whatever. You guys get the point, right? A series of this term divided by the n factorial, and then we're also going to have my x minus a, and remember a is 2, so x minus 2 to that n power. Okay, let's just write out a few of these terms here so we can visualize it. If I were to plug, oh, I guess we could simplify it down as well. That'll make it look nicer anyway, because I kind of goofed it. So by simplifying, I'm saying that the n factorial on the top and bottom is going to cancel out. So just to make it look a little bit nice. So we'll have that negative 1 to the n, or k, I guess is what it really should be. We have the 2 to the n plus 1 that's going to be in the denominator now. And then we have the x minus 2 to the n, to the little n, not the big n. Okay, so now to write out a few of these terms here, if I were to plug 0 into it, I would get 1/2. I'm going to do these pretty quick now. The next one would be negative 1/4 times the x minus 2. The next one would be positive 1/4 times x minus 2 squared. And then it would be negative... oh, we didn't write out what the next one would be, did we? That's okay. We'll just write out kind of the generic one. So then the generic one at n, it's just copying down the sequence there. So it will be x minus 2 to the n divided by that 2 to the n plus 1. Okay, and that's it. So it was asking us to write out the Taylor series for 1 over x. This is the Taylor series for 1 over x. So if it's asking for the Taylor series, it probably wants just that part, just this infinite series that's simplified down a little bit. We'll talk about what these terms mean here when you write it all out here. I'm going to define it right now. But before we get to that, there was one other thing that it asked us to do. It also asked us to tell where our Taylor series converges. So let's talk about that. This is our series. And I know it's kind of hard to tell, but this is actually a geometric series. So just to rewrite this a little bit, so it's a little bit bigger, and that way we have our index values as well. This is the series n going from 0 to infinity of this negative 1 to the n divided by 2 to the n plus 1, and then those x minus 2's to the n. All right, so like I said, this is geometric. We just have to be a little bit careful about what the a and the r are going to be for our geometric series here. And to do that, I'm going to rewrite this a little bit by pulling out a 1/2. So we have this 2 to the n plus 1, but remember that when your index is starting at 0 for geometric series, you want your exponents to just be n's. So in my series here, still going to have the index starting at 0. but now I'm going to pull out a 1/2. This is going to make this just become a 2 to the n in the denominator. Then we'll be left with still the negative 1 to the n. In the denominator, it's just going to be a 2 to the n now. And then we still have that x minus 2 to the n. All right, now all of those have that same exponent of n, so I'm going to combine those all together. So still the series n going from 0 to infinity. We still have the 1/2 out in front, but now combining all of these together that have the same exponent, this is a negative 1/2. Nope, not negative 1 over 22, sorry. And then we still have the x minus 2, and now it's this whole thing to the n power. All right, so just rewriting it, that way we have the a out in front, 1/2, and we have our r value here. So coming down here, our a is just a positive 1/2. The r value, we'll just write it out as it is. It's that negative 1/2 times x minus 2. You can distribute the negative 1/2 in, so negative 1/2 x plus 1 is another way of thinking about the r value there. And remember that this converges as long as the absolute value of r is less than 1. So for us, we're going to be setting the absolute value of negative 1/2 x plus 1 to be less than 1. And remember, whenever you have an absolute value is less than a number, this is where you want to squeeze. So negative 1/2 is less than, negative 1 is less than negative 1/2 x plus 1. And then that less than 1. Okay, and then we just solve. So subtract 1 on all three sides. We're going to get negative 2 is less than negative 1/2 x is less than 0. And now we want to multiply, oh sorry, I have that x in the denominator. It's not supposed to be there. Now we want to divide everything by negative 1/2. And you have to be very careful here because we have these inequalities. Dividing by a negative number is going to flip all the signs. So now it's going to be 1 is greater than x is greater than 0. Or another way of writing that, 0 less than x less than 1. And that's going to be my interval of convergence. You could have done the ratio test to find the interval of convergence. I just thought the geometric test, or geometric series, was a little bit easier to solve this one. So just to kind of quickly talk through this one question again, this one took a little bit longer than I wanted it to. I'll make another video with another example. But you're given a function 1 over x at the center 2, and you want to find the Taylor series. Here's the definition for Taylor series. You have to figure out what your kth derivative is at a. So we took a few of the derivatives to find the generic form of the nth derivative. Plugged in 2 into the nth derivative, it got this. This is the numerator of the fraction for my coefficients out in front. So we wrote out our series, the infinite series of that thing, divided by the factorial times x minus the a to the n power or to the k power. I've gone back and forth between k's and n's, but just know that they're the same thing. Simplified it down a little bit by just canceling out these n factorials, and then we wrote out a few of the terms just so you can kind of visualize what 1 over x is centered at 2. Then it asks us to find the interval of convergence, and I just did geometric here because I noticed that this was a geometric series. We just had to be a little bit careful about the exponents, and then just following along, we get that our interval of convergence is between 0 and 1. Not 0 and 1. Oh no, I think I goofed somewhere. Oh yeah, here. Oh no. All right, go back a little bit. Sorry. I'm sure you all were yelling at me as I was doing this, but 2 divided by 1/2 is actually not 1, it's 4. I promise I'm okay at math. All right, so sorry about that. The interval of convergence should be between 0 and 4, not between 0 and 1, only because I didn't know how to divide by a fraction. Oh, I'm so embarrassed. All right, next video, I'll do one more example.